This is a lecture on the end of chapter 12, and it's great because it ties together what we've learned so far in thermochem, which is how enthalpy affects processes and how changes in entropy affect processes. And we're going to learn in this lecture about something called Gibbs free energy, which is represented with a capital G, and how that ties together both enthalpy and entropy to tell us overall if a process is favorable and is going to occur spontaneously or not. This is an equation you'll be using a lot. So free energy is the amount of energy that's actually available to do work, to do something useful. So remember I talked about the first law of thermodynamics, which is simply energy can either be created or destroyed. And then I posed the question to you, well, if energy is constant, why are we so worried about running out? And that was my introduction to entropy, where I said that although the total amount of energy remains constant in our world, in our universe, it becomes more and more dispersed or diluted and less usable. And that's what entropy measures for us. So overall, if a process is going to occur spontaneously, be favorable overall, we have got to consider both enthalpy and entropy. You can see entropy, it's important what temperature it's at. And just as a reminder, a favorable enthalpy has a negative sign. That means enthalpy decreases during the process. And a change in entropy that is favorable has a positive sign. Now, what we're striving, if we're looking for a spontaneous process, is for delta G, free energy, to be negative. So the sign convention for free energy and enthalpy are the same. Negative means favorable. Entropy is the one that's different. We'll talk more about the sign conventions of enthalpy, entropy, and free energy, but that's going to be a bit tricky when you get into it. So again, this is what we're looking for. So the bottom line is if both enthalpy and entropy are favorable, as in the sign in front of them, if the change in enthalpy and change in entropy, then delta G will be negative, will also be favorable. But you can see that temperature is a big player here. All right, so we'll go through a bunch of examples. This is a Gibbs free energy graph, which will be important for you to be able to interpret. So I always look at the axes first when I'm interpreting graphs. So free energy or delta G, not delta G, just G. So it's not change in free energy, it's just free energy here. And we're looking, typically it's any process, but here's the particular reaction we're looking at here. So what this graph shows you is that G, free energy, is decreasing, okay, with time. So we'll just say time as the reaction proceeds, okay? And we have just learned, right, that when the change in energy is negative, that is spontaneous. Right? So notice it says along here is spontaneous. Then you reach a point where the free energy is as low as it will get for this reaction, okay? And at that bottom point, and we haven't learned much about equilibrium yet, but just kind of plant a seed, that is equilibrium. And at this point, there's no driving force to go either way. Okay, it is the most stable. Remember that the lowest nature favors the lowest possible energy. And so this is the most stable. Now, if the reaction were, if you were try to go beyond equilibrium, whatever that happens to be for this system, it would be non-spontaneous. Okay, so going further toward product, making more product than is present at equilibrium, would be non-spontaneous. This equation should look pretty familiar by now. It's the same formatted equation that we did for change in enthalpy for a reaction and change in entropy for a reaction. We can do the same process to find the change in free energy for a reaction or any process. And so, of course, again, it's products first and then minus reactants. I'm not going to work a sample problem for this because we've already done it for delta H and delta S. Pretty straightforward, but there are a few other equations we can use to calculate the free energy change for any reaction. So you may remember in the first slide, it's probably the most common equation, and this is one that I'd like to see you get real familiar with. I want to point out something that I don't think I mentioned when I first brought up this equation, is that temperature must be in Kelvin. And so remember, if you're given Celsius, which a lot of times you will be, remember the conversion between Kelvin and Celsius. Okay, in this case, the temperature is given in Kelvin, so that's perfectly fine. Also pay attention to the units of enthalpy and entropy. As I said before, entropy is typically given, because it's usually a smaller overall value, is given in joules, and enthalpy is typically kilojoules. So here's another conversion you need to keep under your hat, that 1,000 joules equals 1 kilojoules. Convert them so they are in the same units. Doesn't really matter if you convert them both to joules or convert them both to kilojoules, just depends what the question is asking, or what units a question is asking for. All right, so let's go ahead and plug everything in. Delta H for the reaction. All right, the temperature was given already in Kelvin. Now again, make sure you bracket that T delta S so that the negative sign gets distributed. All right, so here's temperature. And then because entropy was given in joules instead of kilojoules, you can convert it ahead of time, but I just kind of merged it in with the overall equation to convert from joules to kilojoules. Okay, so when you plug all that in, and you may want to enter that in your own calculator, just make sure you're entering things right. I've already talked to a number of you about entering these kind of complicated equations as well as scientific notation correctly into your calculator. It's very easy for your calculator to misread what you're telling it to do, so you may want to punch everything in, and you may want to do that for all the questions that I give you as samples, just to make sure you're using the calculator right. You don't want to find out on the test that you're messing up. Anyway, here's the value, and it happens to be expressed in kilojoules. So here is the heavy conceptual part of this lecture. This is going to take some brain energy. You might have to listen a couple of times. There are all sorts of combinations mathematically that you're going to have to deal with to determine if a reaction is spontaneous or not. You will not always be given numbers. Sometimes you will just be told change in enthalpy enthalpy is increasing, entropy is decreasing, what happens to delta G? And you're like, well, give me numbers and I'll calculate. But you won't always be given numbers. So you need to be able to have a really good grasp on predicting whether delta G will be negative or positive, and at what temperature it may switch from being negative to positive. All right, so remember that enthalpy, my deltas got cut off there. Okay, remember that when you're talking about enthalpy, a favorable situation is when the change in enthalpy is negative. And when you're talking about change in entropy, it is favorable when the change in entropy is positive. So, looking at this equation, if both enthalpy and entropy are favorable, so if enthalpy is a negative, right, and entropy is a positive, that's favorable for both of them, that means that delta G will always be favorable. So where the brain twister comes in is if one, let's say enthalpy is favorable and entropy is not, or vice versa. What if entropy is favorable and enthalpy is not, okay? So that would mean, mathematically speaking, or according to the equation, we would have a situation like this. So let's say enthalpy would be favorable and entropy would be unfavorable. So if they both have the same sign, both positive or both negative, we don't really know, we can't intuit until we have exact numbers what the value of delta G is, if it's going to be negative or positive. And so that is the same for, let's see, if we did delta H unfavorable and delta S favorable. So if they were both positive, same situation. You wouldn't know if delta G is spontaneous or not. It would depend completely on how large the delta H term is compared to the size of the T delta S. And a lot of times what it comes down to is simply the temperature, right? If temperature is high, that means this whole term, T delta S, is going to take on more importance. If the temperature is low, then the T delta S term is going to be much less important. The chart at the bottom of this slide shows all the possibilities. And we have talked about if both delta H and delta S are favorable, then the process will be spontaneous at all temperatures. If they are both unfavorable, the process will be non-spontaneous at all temperatures. Here are the ones that require some real thought. If change in enthalpy is favorable, it's a negative sign, right? Meaning, meaning exothermic. If that's favorable and entropy is unfavorable, meaning entropy is decreasing, it will be spontaneous at low temperatures and non-spontaneous at high temperatures. So take whatever time you need to understand that and be able to explain it and interpret it. So let me explain it this way. So we're going to take the case where they're both negative. All right. So what you want to do is determine which one is favorable. In this case, the favorable one would be delta H. And you want that to be the maximum value if you want a spontaneous. So how do you get delta H to be the more important factor? How do you get it, ensure that it's more important than the entropy factor? Well, you want to minimize the unfavorable factor, right? So how do I minimize the importance of delta S, any change in delta S? I do it by minimizing temperature. So at low temperature, this situation will be spontaneous because we have minimized or made much smaller the T delta S term. And so the favorable term dominates. Looking at the other end of the spectrum, if delta S is favorable, okay, so delta S increasing is a favorable, and delta H is unfavorable, if it's endothermic, then looking at the equation, mathematically, with plus and minus sign, we have a situation like this. Okay, and again, you want to minimize the unfavorable portion of the formula if you're trying to get spontaneity, right? And you want to maximize the importance of the favorable. So again, you really have no control over the delta H. It is what it is. But the delta S term, because it has the temperature involved in it, you can maximize the effect of the whole T delta S term by increasing temperature. And so in the situation here where entropy is favorable and enthalpy is not, a high temperature will result in the reaction being spontaneous. Again, you might need to go through that carefully on your own a couple times or try reading it in different sources until it really sinks in and you get it and you're able to explain it. Let's go through a specific example where enthalpy and entropy are at odds with each other and show you how spontaneity depends in that case on the temperature. we're going to think about melting an ice cube again. Okay, melting of anything is an endothermic process. It requires an intake of heat to occur. And so enthalpy of that process, of any melting process, is unfavorable, has a positive value, endothermic. However, we have talked before about when you melt something, entropy increases, okay? The water molecules are getting more freedom of motion as they pass from the solid state to the liquid state. And so the change in entropy is favorable, the positive sign. So you have the situation now that I showed you just a minute ago where they're each the same sign, they're each positive. But you would like the favorable term, which is the T delta S, you would like to maximize it so that delta G has a better chance of being spontaneous. How do you maximize the favorable term, T delta S? You increase temperature. So what that is saying then is at high temperatures, melting should be favorable. We know that to be true, right? At high temperatures, melting will be spontaneous, while at lower temperatures, melting will be non-spontaneous. That's exactly our experience, right? If you put an ice cube in the freezer, it is not going to melt spontaneously. So at low temperatures, delta G is positive and it's not spontaneous. And we can show you that with the actual formula and numbers also. So this particular sample problem says to calculate free energy at both 10 degrees Celsius and minus 10 degrees, right? Now we know that at minus 10 degrees, the ice is not going to melt. And then at positive 10 degrees, anything above 0 degrees Celsius, it will melt, right? So we should be able to see that in our formula. So let's go ahead and plug in these temperatures into our free energy formula and see what happens. Now remember that temperature has to be in Kelvin. So we need to convert the 10 and minus 10 to Kelvin. So just real quick so you know where the numbers are all coming from. All right, so here are our two temperature values that we're going to plug in. So these are simply the values, you'll be given the values. Delta H for melting of ice, 60-30 joules per mole. Here is, this is at a temperature of minus 10 degrees Celsius. And here is the value for change in entropy for melting of ice. When you plug all that in, the value you get for delta G is 218, but the point is it is a positive value. Positive delta G values mean it is a non-spontaneous process, which you already know, right? We know the ice is not going to melt at negative 10. Now let's see what happens to the value for delta G when we plug the information into or at a temperature of 10 degrees Celsius above the melting point of ice. So the only thing that changed here is the temperature is now 283 Kelvin. The value we now get for delta G is a minus value, which means that the melting of ice at 10 degrees is a spontaneous process, all right? So again, when the signs of delta H and delta S are the same, either both positive or both negative, that it means there are odds with each other. One is favorable, one is not. The deciding factor on spontaneity is temperature. Temperature matters. So we've talked about calculating free energy from a couple different equations. We've talked about calculating it from that familiar equation we have now, where sum of free energy of products minus sum of free energy of reactants. That's one way. And another way, the more common way, is from the equation delta G equals delta H minus T delta S. And kind of combining those two equations in a way, but just kind of give you a heads up, so because you probably will encounter problems like this. Sorry, what if you're given a problem and it asks you to calculate free energy But instead of giving you the actual enthalpy change for the reaction and the entropy change for the reaction, it gives you a bunch of enthalpy of formations and entropy of formations. So again, this is when you have to pay attention to the suffixes. Why did I say suffix? To the subscripts, right? So in order to use this equation for free energy, you need delta H of reaction and delta S of reaction, okay, not formation. If you're given the formations for each of the reactants and products, that means it's a two-step calculation, all right? So the first step, you would have to calculate delta H of reaction by using the summation heat of formation of products minus heat of formation of reactants. And so that would be like step one. You would get the enthalpy of reaction with the formations. Step two, you'd have to do the same thing to find entropy change of reaction. In other words, you would have to take the sum of entropies, you can say entropy of formation or just absolute entropy of products minus entropy of reactants. Okay, and so once you would have the enthalpy and entropy of reaction, then you could calculate the free energy from the first two values that you calculated. So it's really three separate calculations. Tedious, but. Alrighty, so here it is actually worked out. Step one, again, finding the enthalpy of reaction from the enthalpies of formation. And then doing the same, find the entropy of reaction from the absolute entropies of products and reactants. Now again, look at the units. And enthalpy is almost always in kilojoules and entropy is almost always in joules. So you need to make those match. So converting the joules to kilojoules, remembering that temperature here is in Kelvin, okay? And you know what a negative value means, right? So that is a spontaneous equation. And that is it for this PowerPoint.